This is problem 30.15, and here we talk about motional EMF. So we're told that we have a conducting bar of length L here, moving to the right on two frictionless rails as shown in this image. A uniform magnetic field directed into the page, like this, has a magnitude of 0.3 teslas. Assume the resistance here is 9 ohms, the length here is 0.35 meters, and then we're asked to figure out at what constant speed should the bar move to produce an 8.5 milliamp current in the resistor. And we know a couple things here from the theory video I did a little while ago. So here we know that E, this is just Ohm's law, V is equal to I times R, so the EMF is equal to I times R. We also know that for this specific scenario in a motional EMF, whenever we have a uniform magnetic field, E, the EMF that's being induced, is equal to B times L times V. Putting these two together, we get BLV is equal to I times R. All we have to do is solve for V. So V is equal to the current we want, 8.5 milliamps. And then we have resistance of 9 ohms divided by 0.35 meters times 0.3 Tesla, and that gives us 0.729 meters per second. Okay? B then says, what is the direction of the induced current? Now we know that here, in this region, this is where we're looking at the flux, right? We're seeing, okay, this is our closed path whenever the yellow, so the conductor, is at this position. We know that it is opening. When it opens, it means that we have an increase in flux pointing in this direction, because remember this here, this magnetic field is everywhere. So whenever this moves to the right, the flux going through the region that encloses it here increases such that it is going into the page even more. So that means we need to be inducing magnetic field that is out of the page to balance it out. That's Lenz's law. So the flux is into the page and increasing. The current will produce a flux that is out of the page. In what direction is that current going to be? Well, we can use our second right-hand rule because we want to have this essentially inside here. So then if we use our right-hand rule, we see that this is going to happen whenever we have current going counterclockwise. So whenever we have current going like this, we use our right-hand rule, and then we see that we have magnetic field lines coming up out of the page like so, right? So the current is going in the counterclockwise direction. Next, we have C. It says, at what rate is energy delivered to the resistor? This has nothing to do with this chapter, but it's going back from quite a while ago now, where we have P is equal to I squared times R. So P is equal to 8.5 times 10 to the negative 3 amps squared times 9 ohms, and that's equal to 0.65 milliwatts. The next question is kind of interesting. It says, explain the origin of the energy being delivered to the resistor. It's a good question because it's like, we don't actually have a battery, right? Whenever we had a battery, we had a decrease in that chemical potential that was being essentially transferred into that resistor. Here, what we do have, however, is something that's pulling our yellow bar here, our conducting bar, to the right. So there is this force. We have this applied force, right? So essentially work is done by the external force here, and then that energy, or that work, is then transformed into internal energy here. So it's not like you magically get some power here or some work being done here or delivered to the resistor. You actually have to do something to move that conducting bar. So essentially, instead of having a chemical potential that's doing the work, you have some applied force doing that work for you. Okay, and that is it for this question.